Let us continue the miscellaneous exercise of chapter 1. Question number 8. Given a non-empty set X, consider P of X, which is the set of all subsets of X. Define the relation R in P of X as follows. For subsets A, B in P of X, A is related to B if and only if A is a subset of B. This is if and only if. Is R an equivalence relation on P of X? Justify your answer. So P of X is the power set of X, set of all subsets. For example, X is the set 1, 2 say. So power set of X will be set of all subsets, null set, set 1, set 2, and then 1, 2. This is the power set. So we are taking two sets. For example, A is this, B is this, say. So A is related to B if A is a subset of B. 1 is a subset of 1, 2. So to make you understand P of X, I wrote this example. Now let us write the proof. We know that every set is a subset of itself. Therefore, A is related to A for every A belonging to the power set P of X. Therefore, R is reflexive. Now let us check whether it is symmetric or not. Let A be related to B. That means A should be a subset of B. If A is a subset of B, B need not be a subset of A. Unless they are equal, B won't be a subset of A. See, for example, 1 is a subset of 1, 2, but 1, 2 is not a subset of 1. Okay, therefore, R is not symmetric. If it is not symmetric, I can conclude that R is not an equivalence relation. But it is a transitive relation. See, if A is a subset of B and B is a subset of C, definitely A will be a subset of C. It is a transitive relation. You don't have binary operation questions. Now question 10. Find the number of all onto functions from the set 1, 2, 3 up to n to itself. Now see example 46. Find the number of all 1, 1 functions from set 1, 2, 3 to itself. This is 1, 2, 3 set to 1, 2, 3 set, let us take. So number of 1, 1 function. 1 can be connected to any one of these three elements. So 3 ways are there to connect this. For this element 2, you have two leftover elements in the codomain. So this has 2 ways to connect. And only one element will be left in the codomain now. So it has only one way. This is nothing but the permutation of these three elements 1, 2, 3. Therefore, number of 1, 1 functions will be 3 into 2 into 1, which is 3 factorial. Similarly, we can do this question. Here the set 1, 2, 3 to n to set 1, 2, 3 to n. So 1 can be connected to one of these n elements in n ways. 1 can be connected to 1, or 1 can be connected to 2, or to 3, or up to n. So n ways are there. Now remaining n minus 1 elements will be there here. Therefore, 2 has n minus 1 ways to connect with. For 3, n minus 2 ways, etc. The last element will have only one way. only one element will be left in the codomain. If a relation is defined from a set to itself, and if it is onto, it has to be a 1-1 function. If a function is defined from a set to itself, and if it is onto, it has to be 1-1. We did this in example 13 and 14. Similarly, if it is 1-1, it has to be an onto function. Therefore, number of onto functions will be same as number of 1-1 functions. That is nothing but the permutation of these n elements. So it will be n into n minus 1 into n minus 2 up to 1, which is n factorial. Question 11. S is the set A, B, C and T is 1, 2, 3. Find F inverse of the following functions from S to T if it exists. F is given as, it is given in roster form A3, B2 and C1. This is a 1-1 and onto function. See, this is set S, set T, A, B, C and 1, 2, 3. A is connected to 3, B is connected to 2, C is connected to 1. So F is 1-1 and onto. It is 1-1 because distinct elements have distinct images. It is onto because every element of the codomain has a pre-image in the domain. Mention these reasons. Therefore, F is invertible. And we can write F inverse, which is 3A, 2B and 1C. Second subdivision. F function is given as A2, B1, C1. From the elements B1 and C1, we can say that it is not a 1-1 function. So elements B and C have the same image. Therefore, F is not 1-1. Therefore, F is not invertible. Question 15. Let set A is equal to -1, 0, 1, 2 and set B is equal to -4, -2, 0 and 2. F and G are from set A to set B. Be the functions defined by f of x is x square minus x for all x belonging to A, and g of x is 2 times absolute value of x minus half minus 1 for all x belonging to A. Both are defined on the set A. Are f and g equal? Justify your answer. So we will calculate f and g. Both are defined on set A, so we have to find both the functions for all these 4 elements of A. So let us find f of -1, -1 the whole square, minus of -1. The answer is 2. Now f of 0, 0 square minus 0, which is 0. F of 1, 1 square minus 1, 0. Now let us calculate f of 2. 2 square minus 2, which is 2. G is also defined on the set A. So G of minus 1 is equal to 2 times minus 1 minus half is minus 3 by 2. So it becomes 3 minus 1, 2. Then G of 0, 2 times 0 minus half minus 1. So this becomes plus half, 2 gets cancelled, 1 minus 1, the answer is 0. Then for the third element, G of 1, 2 times 1 minus half is half, so 1 minus 1, 0. Then for G of 2, 2 times 2 minus half, 2 minus half is 3 by 2, minus 1, so 3 minus 1 is 2. Now look at the answers. The answers are same. Therefore, I can say that F is equal to G. Question 16. Let A is equal to 1, 2, 3. Then number of relations containing 1, 2 and 1, 3. So let me write one relation containing 1, 2, 1, 3, which are reflexive, symmetric, but not transitive. So it has to be a reflexive relation. So it becomes reflexive only if you have 1, 1, 2, 2, 3, 3. Then symmetric. 1, 2 is there, so 2, 1 also should be there. 1, 3 is there, 3, 1 also should be there to make it symmetric, but not transitive. Now see this 3, 1 and 1, 2. We have these two elements in this set, but 3, 2 doesn't belong to R. Therefore, it is not transitive. So I wrote one relation which is reflexive, symmetric, but not transitive. Let me check whether I can write one more relation satisfying the given condition. In case if I include 2, 3, I have to include 3, 2 also to make it symmetric. In that case, it becomes a transitive relation because I have written all 9 elements, because A cross A has 9 elements, right? So I have written the universal set. Universal set is reflexive, symmetric as well as transitive. Therefore, only one answer can be written. The answer for this is A. Question 17. Let A is equal to 1, 2, 3. Then the number of equivalence relations containing 1, 2. Equivalence relation means it has to be reflexive, symmetric and transitive. So to make it reflexive, I have to include 1, 1, 2, 2, 3, 3. Since 1, 2 is there, I have to include 2, 1 to make it symmetric. It should be transitive also. If I take 1, 2, 2, 1, 1, 1 is there. Similarly, 2, 1, 1, 2, 2, 2 is there. Therefore, it is transitive. So this is an equivalence relation. Let us try to write one more. 1, 2. It has to be reflexive. So 1, 1, 2, 2, 3, 3 should be included. To make it symmetric, I have to include 2, 1. Let me include one more element. If I include 1, 3, 3, 1 should be included to make it symmetric. If I consider these two elements, 2, 1, 1, 3 are there in R2, but 2, 3 is not there. Therefore, to make it transitive, I have to include 2, 3. If I include 2, 3, I have to include 3, 2 also, so that it becomes symmetric. This is the universal set, A cross A. Only two equivalence relations can be written containing the element 1, 2. The answer is B. Question 18. Let f be from R to R be the signum function defined as f of x is equal to 1 when x is greater than 0, 0 when x is equal to 0, minus 1 when x is less than 0. And g is a function from R to R, be the greatest integer function. So g of x is the greatest integer function. Then, does f composite g and g composite f coincide in open at 0 and closed at 1? Let us give a counter example for this. Let me take half. I will calculate f composite g of half, which is f of g of half, f of g of half. G of half is greatest integer function of half. Greatest integer function of half is 0 and f of 0 is 0. Look at this definition. Calculate g composite f of half. G of f of half, g of f of half. Half is greater than 0. So we will use greater than 0 definition, which is 1. And g of 1 is greatest integer function of 1 is 1. They are not the same. Therefore, I can conclude that f composite g is not equal to g composite f. Whereas, if you take the element 1, both will be same. So I told you, look for a counter example for which the functions are not the same. Example 41. If R1 and R2 are equivalence relations, R1, R2 both are equivalence relations in a set A, show that R1 intersection R2 is also an equivalence relation. So we have to show that R1 intersection R2 is reflexive, symmetric as well as transitive. R1 and R2 are equivalence relations. R1 and R2 are reflexive, symmetric and transitive. So R1 and R2 are reflexive. Therefore, A, A belongs to R1 and A, A belongs to R2 for every A belonging to A, because they are reflexive, which implies A, A belongs to R1 intersection R2. Therefore, R1 intersection R2 is reflexive. We are going to prove that it is symmetric. Let us take an element AB belonging to R1 intersection R2. We have to show that BA also is there in R1 intersection R2. This implies AB is a common element. It belongs to R1 and A, B belongs to R2. If AB is in R1, BA will be in R1 and BA will be in R2 also. The reason is R1 and R2 are symmetric relations, which implies BA is a common element. Therefore, it will be in R1 intersection R2. Therefore, R1 intersection R2 is symmetric. Now let us check the transitive condition. Let AB and BC belong to R1 intersection R2, which implies AB, BC belong to R1 and AB, BC belong to R2. And we know that R1 and R2 are transitive relations. So if AB, BC are in R1, then AC will be in R1. Similarly, R2 is also a transitive relation. Therefore, AC belongs to R2. Now, AC is in R1 as well as R2, so it becomes a common element. Therefore, AC belongs to R1 intersection R2. Here I will write the reason for this step as R1, R2 are transitive. Therefore, R1 intersection R2 is transitive. All three are satisfied. Therefore, R1 intersection R2 is an equivalence relation. Example 42. R be a relation on the set A of ordered pairs of positive integers defined by x, y is related to u, v if and only if xv is equal to yu. See how the multiplication has been done? xv is equal to yu. Show that R is an equivalence relation. Okay, let us check whether x, y is related to x, y. Check that multiplication. X, y is related to x, y as xy is equal to yx. And it is true for any element x, y taken from the set A. Therefore, R is reflexive. Let x, y is related to another element u, v, which implies x into v should be equal to y into u. Which implies I can write this as, see, I have to get uv is related to xy. That is, u into y should be equal to v into x. U into y is equal to v into x. Both are same equations. These two are same. Therefore, I can say that u, v is related to x, y. And this is true for any two elements x, y and u, v taken from the set A. Therefore, R is symmetric. For transitivity, we will consider x, y related to u, v and u, v related to another element, the third element. Let us take it as a, b. This implies x into v is equal to y into u and u into b is equal to v into a. Now let us multiply these two equations. xv, multiply the left hand side, xv ub should be equal to yu va. U and v are getting cancelled. We get x into b is equal to y into a. Therefore, I can say that x, y is related to a, b. Check this multiplication. X into b is equal to y into a. It's correct. And it is true for any three elements taken from the set A. Therefore, R is transitive. So we have proved that it is reflexive, symmetric and transitive. Therefore, R is an equivalence relation. Let's do the next example sum. Example 43. X is the given set 1, 2, 3, 4, 5 up to 9. R1 be a relation in X given by R1 is equal to set of all X comma Y such that X minus Y is divisible by 3. R2 be another relation on X given by R2 is equal to set of all X comma Y such that the set XY is a subset of 1, 4, 7, or it is a subset of 2, 5, 8, or X comma Y is a subset of 3, 6, 9. Show that R1 is equal to R2. If you see the elements of these three sets, difference between the elements taken from a set is divisible by 3. For example, 7 minus 4 taken from the first set, 3 divisible by 3. Take any two elements here. 8 minus 2, 6 divisible by 3. Here take any two. 9 and 6. The difference is divisible by 3. Let us take X comma Y belonging to R1, which implies X minus Y is divisible by 3 by the definition of R1, which implies X comma Y is a subset of 1, 4, 7. Actually, these are the partitions of the given set X. Or X comma Y should be a subset of 2, 5, 8, or X comma Y set should be a subset of 3, 6, 9, which implies X comma Y belongs to R2. Therefore, I can say that R1 is a subset of R2. This is our first result. Similarly, we will try to prove that R2 is a subset of R1. Therefore, we conclude that R1 is equal to R2. Let us take an element X comma Y from the set R2. Which implies the set X comma Y is a subset of 1, 4, 7, or X comma Y is a subset of 2, 5, 8, or the set X comma Y is a subset of 3, 6, 9, which implies X minus Y is divisible by 3, because if you take any two elements from these sets, the difference is divisible by 3. Therefore, X comma Y belongs to R1. Therefore, R2 is a subset of R1. Mark this as second result. So from 1 and 2, R1 equals R2. Example 50. Consider the identity function in from n to n defined as in of x is equal to x for every x belonging to n. Show that although in is onto, but in plus in from n to n defined as in plus in of x is equal to in of x plus in of x, which is equal to x plus x 2x. We have to show that this is not onto. It's a very simple question. So I am drawing the figure for in plus in. It is from set n to n, 1, 2, 3, 4, 5, etc. 1, 2, 3, 4, 5, etc. For 1, it is 2x. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6, etc. Now, if you see, the images are all even numbers because of 2x. So, for odd numbers, we don't have pre-images. So, you can write that reason. You can give one counter example. So, 3 belonging to n doesn't have pre-image in the domain n. Under in plus in. Therefore, in plus in is not onto. But in is onto because it is an identity function. See this function? In is an identity function. Definitely it has to be an onto function. In is onto, but in plus in is not an onto function. Example 51. Consider the function f from closed interval 0, pi by 2 to r given by f of x is equal to sin x. And g is another function from this closed interval 0 to pi by 2 to r given by g of x is equal to cos x. Show that f and g are 1, 1, but f plus g is not 1, 1. See the domain for both the functions, it is the first quadrant. So in the first quadrant, for different angles, we get different values for sine as well as cos functions. Let f of x1 is equal to f of x2. That is, sine x1 is equal to sine x2. Therefore, x1 is equal to x2. If x1, x2, they belong to the first quadrant. If first and second quadrants are included, we may have the same values. For two different angles, we will get the same value. Okay, but in this first quadrant, for different angles, we get different sine values. Therefore, it is a 1, 1 function. Similarly, we can show that g is also a 1, 1 function. Let g of x1 is equal to g of x2. Cos of x1 is equal to cos of x2. So x1 must be equal to x2 because x1, x2, they both belong to the first quadrant. Therefore, g is 1, 1. Now we have to show that f plus g is not 1, 1. Let us calculate f plus g of 0. This becomes f of 0 plus g of 0. That is sine 0 plus cos 0. Sine 0 is 0, cos 0 is 1. The answer is 1. Calculate f plus g of pi by 2, which is f of pi by 2 plus g of pi by 2. Sin pi by 2 plus cos pi by 2. Sin pi by 2 is 1, cos pi by 2 is 0. The answer is 1. So for two different values, we get the same answer 1. That means it is not a 1-1 function. Therefore, f plus g is not 1-1.